a little bit about my journey, like how I got here. So I was born and raised in Maryland, great state, great childhood. I went to school, undergrad at Clark Atlanta University in Atlanta, Georgia. And then I went up to do my graduate degree, master's and PhD at MIT in the Computer Science and Artificial Intelligence Lab. And while I was at MIT, I had the opportunity to work on 3 projects in Africa, 2 of them in Ghana, including deploying the very first fab lab on the continent of Africa, and then one of them in Kenya, in central Kenya. And from that experience, plus sitting with robots, so a little bit of human, a little bit of humanoid, from that experience, I just really knew that being on the continent is a researcher's and an entrepreneur's dream. I can think different. The structures are not necessarily the same. The problems might be similar, right? But I can think different, collaborate with a whole new set of brilliant minds. And I knew that I wanted to at least be abroad and ideally on the continent. So after I graduated, I had the opportunity to work in Spain for a couple of years, working around smarter cities types of solutions. And then I was able to be a part of one of the first corporate research labs on the continent based here in Kenya. And now I've been here for basically about a decade. So that's my journey and how I got here. So I've done a lot of projects on the continent. As you saw, I've done quite a bit of work in the healthcare space, which was not my background at all, but I completely love it. And I'm so passionate about it just by exploring it in the different communities that are addressing those big problems. Also working in transportation to fix Nairobi's traffic. Was it fixed? Okay, not yet, but it's been amazing. I worked on it like 9 years ago, so progress is happening. And also working in climate and water. And there's been quite a bit of lessons learned from myself and my colleagues. And I just want to highlight 3 considerations here that kind of are sub-themes. I'm sure it affects more than just the continent, but sub-themes that have come out of the work that we've done in collaboration with different organizations. So limited or no access to data. So I know everyone always complains about the data problem, but generally there is a bit of data around the continent. It's about accessing it. A lot of it is in silos. Different institutions may not even know about each other or know about the studies that are there. So there's actually quite a bit of data. So there's some element of innovation we have to think about there to get access and to get that information known. The second is, what are the systems, the infrastructure, the ecosystem? Who are the partners? You know, in Africa, we have a lot of NGO partners, we have government partners. So who are these players that we need to be interacting with as we deploy AI systems? So you might deploy a system that, you know, tells you to get out of a certain area. Maybe it's a warning system, but what does that mean if all the population is on the roadways for a certain period of time? So there is an underlying, you know, systems problem that sits here, and who are the stakeholders you need to interact with to make decisions on that? And the last, of course, is trust and bias in AI. So thinking about who created the AI and who are the consumers and the beneficiaries of AI. These are things that have come out through conversations of working with different organizations, scientists, academics on the continent. And you'll see a little bit of this in the work and from also my colleagues' presentations later. All right, so I'll just give a flavor of 2 concrete real-world examples where AI has been used for societal impact, addressing big challenges. One on malaria control, so decision support, broadly decision support for disease intervention planning. And the second on early warning systems for flood forecasting. I'll spend a bit more time on the malaria control with some AI flavor in there to get everybody on the same page. We have a 5-minute AI course, and then highlight the flood forecasting and another aspect of AI that is used to make that work possible. All right, so these are the numbers basically that came out of 2020 report on malaria. Unfortunately, everything has gone back up. So we now have an increase in cases. Of course, the continent is the one that's most burdened with that. We have an increase of deaths in malaria. And actually the majority of those deaths are under 5 child mortality, I think almost 80% or more. And it's really challenging because the trend has been kind of flat. So there was a lot of progress, but it's flat in terms of, getting the number of cases down. So there's less investment in malaria control. And so governments have to actually be innovative and think about what are the right strategies given this cost-effective or this cost challenge that they have at the same time, but they also have the burden of disease. What's interesting about malaria is that it's an age-old disease, right? It's been on every continent in the world except for Antarctica, although with climate change. So, and it actually was eliminated in the United States in the 50s. So for me, I would think that's not too long ago, through proper drainage, infrastructures, window screens, and so forth. So different countries have been using various strategies to eliminate or minimize the spread of this disease. Also, what's very important about it, so you see how many deaths and cases there are, but it actually can be treated with anti-malarial drugs, and the transmission can be prevented with effective control. So that's the key there. So what we did is we set out to really understand this problem in collaboration with the Gates Foundation. They had a number of broad questions on, how AI can be leveraged to address this big problem, especially as we're seeing lower investments and still now this very high disease burden. And so one of the questions is, are there other intervention plans or programs that governments and different districts could be applying that might be more cost-effective or better based on their context? So this problem was formulated in such a way. You have your set of decision makers, and your decision makers have a set of goals like reduce mortality, eliminate malaria, reduce prevalence, and then they also have constraints. So you have your budget constraints, you have supplies, and many other constraints. The good thing about malaria is actually it has a quite vibrant modeling community that's been around for decades, so a number of research institutions. And this is an example of one such work by Kaware and others, where they're modeling the life cycle of the mosquito, right? And you can't really see it too well, but in blue, those are points of interventions, whether you're larviciding in a waterbed or if you're providing a net to someone while they're sleeping. So all those different points of interventions in order to control the disease. And we see commonly spraying around buildings, larviciding, even giving medicine to pregnant women to help prevent malaria. So with this general formulation, it actually turns out it's well suited for AI. This is what us in the AI community love. It is a complex decision problem with theoretically an infinite search space of possibilities, right? So do I do spraying? Do I offer bed nets? Do I do case management? If so, which combination thereof, which proportion of the population? So it's actually a complex problem, but very well suited for AI. And in this case, it's actually very well suited for reinforcement learning, which is a subset of AI that helps with decision-making. So basically you have an agent or some sort of AI algorithm that's exploring in a simulation environment. So a simulation environment, you put the inputs in, you're forecasting out what might happen in the future scenario, the number of cases. And you say, well, given these actions and given this future state, was this a good decision? And so now you can have these different AI agents explore this environment by doing this formulation. So here's one example that we did that's in this paper here, is looking at, let's say, one shot or single step decision making. What is the set of interventions that should be applied for a certain community that has the best reward? In this case, our reward was cost effectiveness. Cost per disability adjusted life year. And the actions that we looked at were deploying bed nets or spraying across different buildings and structures and so forth. So you can imagine what you're really looking for is percentage of population. So 10% get nets, 50% of households get sprayed, that kind of search. And the environment we used was an open source environment called Open Malaria. And it's an agent-based environment that is representing the world based on where it's calibrated. In this case, it was calibrated in Western Kenya. And it has noise in it, stochasticity and uncertainty within it. But basically, you try this range of interventions and you forecast what the world or what that location in Kenya would look like if you apply these interventions. So as it turns out, that enabling these AI agents to explore the intervention space, we actually are able to answer the question that the foundation gave us. So on the right, you see all these data points in which various AI agents explored this simulation environment to look for, you know, the best reward in this environment, right? So which combination should I try to get the best reward for this location? And as it turns out, there was work earlier done in this on that same exact model, but in a different way, where you had the domain experts working together with modelers and with the local government. And the domain experts basically said, I think you should try this range of nets and this range of spraying, right? So essentially, you get tens of experiments, and then you forecast out and you say, okay, this is the best experiment. In that case, that's this one, this black dot up there, Stucky et al., where you have about 55% IRS is the spraying, indoor residual spraying, and ITN is insecticide treated nets. So 55% of the population to have nets, and then 70% to be sprayed, okay? But and then there's the expert human who says, this is the best decision, right? And this is actually quite traditional. But as we reformulated the problem as a reinforcement learning problem, we now were allowed to bring the AI community and apply various algorithms to explore this nearly infinite space and find actually more cost-effective intervention plans. So this is huge in terms of bringing AI into this global health community and seeing that it is possible, not alone with AI, but with the decision makers to help inform their decision making and to explore the space more. We also have some later work where we were exploring, okay, that was one shot. So what should you do now? Here's a set of interventions, go do that, and that will be great. Well, what happens is traditionally governments basically take about a 5-year timeline to develop a malaria intervention program. Here's what we're gonna do. And then you go implement and you do your M&E, your monitoring and evaluation. Well, 5 years could be brittle. The environment can change a lot. So what if you're able to break the 5-year timeline up into different discrete time points and change your intervention plan? So this is a notion of sequential decision-making, really taking advantage of the full force of reinforcement learning. So in our case, we took a place where the goal is 5% mosquito prevalence. You want to reduce to 5%. That's the red line. And then, you know, we run all these samples. So the orange and the blue are samples. The blue representing this one shot over that timeline, and then the orange representing this, hey, I'm going to change the plan every year. Well, as it turns out, even that approach got us better rewards in the sense that it was more cost effective to change that plan throughout your 5-year timeline for planning. So again, showing the promise of these techniques in AI for global health. So a lot of this work was done with many people, with academia, with our partners in the foundation, with their collaborators, in order to even understand the space, especially if you're coming as a computer scientist to the space. And what we've done is we built this platform that's open source. You can see it there, but the platform actually has tools for both domain modelers. So domain modelers are anybody who's implementing models like malaria models, COVID models. You actually can even do climate models or financial models, anything where you're forecasting out and you have a range of interventions. Policymakers, so they can explore the space, say what their goals are, and work together as a team and adapt much more flexibly. And then and also bringing in the AI community. So bringing in the AI community to bring their techniques to explore these different models in an efficient way. And to do that, we engaged with the AI community that Vukosi mentioned, Indaba in 2019, which was very big and successful because now they're doing AI on problems that they actually face. We worked with another AI community, KDD, which was very big. We're much more teams there. It's a very high tier AI conference and also presented at NeurIPS, another high AI conference. But the idea was to break the silos in which we were in because the disease modeling community already exists. They have beautiful models there, and AI is actually enhancing or amplifying the power of their models by richly exploring the space of what's possible. And then just as an example case study that one of my colleagues is still leading and featuring who's here, is in Uganda. So the goal for Uganda, remember I mentioned you have this 5-year timeline, you have some funders. This is the scenario that the policymakers are in. The goal for Uganda was to reach a certain target prevalence of 5% or less in 134 districts. Now imagine every district and the environment and the number of cases is different. So that's a huge decision-making problem for a policymaker. And that's why it's very important to have these types of tools in which we can enrich and enhance the models that already exist, but also help and work together with the policymakers on their decision-making. So let me just do one highlight of some other work that's also quite impactful. And it's been implemented in the global South in 5 countries, in Colombia and Brazil and in India and Bangladesh and another one I don't recall. And this is around flood forecasting. So believe it or not, flood forecasting or floods are actually one of the biggest, or if not the biggest natural disaster that happens so frequently. And you have tens of thousands of lives that are lost and hundreds of millions of people who are affected every year by flooding. At the same time, of course, if you had a warning or an understanding that floods were coming, you can react individually and the government can react to support you. So this work is around giving timely alerts for forecasting floods. Specifically, the aim of the work is to provide accurate and actionable flood alerts that cover all those who are affected by floods globally. So there's an element of scale of alerts. And what we do here is leverage deep learning models, specifically temporal-based ones like LSTMs. You can look it up if you're not familiar or talk with your colleagues. And this helps us to forecast or improve the existing models for hydrological models and inundation models. And that tells you about the amount of water in a volume for a river or any type of waterbed over time. The focus originally was around river floods. And then we are able to use this forecast, which is up to 7 days out, and provide alerts to communities that are potentially impacted and affected. So here's a conceptual diagram of how that works in identifying, who might be affected or impacted by floods over time, and how we can inform the public. And the current work so far is it's actually deployed. It's out there, as I said, in 5 countries, still growing and scaling, covers 370 million. And we've sent 150 million warnings in this context. So one thing to think about when I think about this problem is data sources. So this slide, I was like, what are the red dots and what are the blue dots? They're actually time, and it's vast, from 1919 to 2025, right? So you can see Africa, it's red. That's 1919 to 1985. That's measurements at different water points, basically, around the continent. And then you can also see where all the blue areas are, so the most recent data, right? And so thinking from the AI community, you're training, of course, on the blue, and you have very little information about Africa. And so this also tells you elements about thinking about bias and data at the same time, right? And so broadly, these two show good examples of the interplay of the real problems that we face globally. So there's a clear climate and health impact challenge where you see here in the CNN article, they talk about the flooding that just happened in Pakistan. And the fact that now there's the floods and there's now a plethora of disease, including malaria and all the waterborne diseases, diarrhea, and so forth. And now it's about access to care. So this requires a broad cross-disciplinary community to address this problem. That's it. That's it. Thank you.